Hi everybody, it's Ajanette and I am here to do your Chapter 8 lecture with you. Your Chapter 8 lecture is actually, I'm going to introduce you to our first hypothesis testing, which is a means of testing our hypothesis, and we're going to be using inferential techniques. So this will be our very first introduction into using inferential statistics, where we're using data from a sample to draw inferences about the larger population. And in this case, our technique is going to be z-score. And so what it will build upon everything you've learned in Chapter 5, understanding what a z-score is, how to calculate it, and then it'll carry on into, you know, when you look at the probability chapter and the sampling distribution chapter, those are kind of the bridge that now allows us to use inferential techniques and rely on that unit normal table to make predictions as to what the probability is of getting our score based on that normal distribution. And so we will use all of that information as our foundation for inferential techniques. This chapter is going to be a lot of kind of jargon thrown at you. So some vocab to remember. I recommend that you kind of write out note cards and do a lot of note taking as you're reading the chapters, as you're listening to the lecture. You're gonna really need to process it on a deeper level in order for it to kind of sink in, for some light bulbs to go off and the dots to connect, okay? Okay, so let me go ahead and share my screen. And I am going to open our presentation. And so here we are on Chapter 8. Let me go ahead and launch the presentation view. Okay, so when we're talking about hypothesis testing, it is just that. We are now going to get into testing hypothesis. Remember at the very beginning, I said this is not a math class. It is a research methods class. So all the math, quote unquote, that we use, all the statistics that we use, it's bedded in research methodology. Our whole point in utilizing these techniques is to test hypotheses. And different techniques allow you to answer different questions based on the data. So part of this class is figuring out what type of research questions or data is going to determine, or what type of technique am I going to use based on the research question being asked, the research design being utilized, and the data being collected within that research study. All of those factors influence your research, your inferential technique, your statistical technique that you're going to use. We're only going to learn two. We're going to learn a z-score comparing an individual to a group, or comparing a group to a population. So that's it. Those two. We're comparing an individual to a group, or we're comparing a group to the population, a sample to a population, okay? Okay, so when we talk about hypothesis testing, we're talking about a process that we go through for all statistical methods. So this is not just going to apply to Chapter 8, it's going to apply to 9, 10, 11, every chapter moving forward. We're going to follow the same steps that are going to be outlined. And what it's doing is it's allowing us to evaluate a hypothesis about a population. So it's a procedure that we go through as researchers to analyze the information we have about our sample and to draw inferences about our population based upon that sample. And so in this particular chapter, we're going to use z-scores, relying on what we learned about probability and the sampling distribution of means, in order to compare a sample to a population. So we have a research question hypothesis, and then we can test that hypothesis by comparing the data in our sample to the respective population data. So it's a very consistent process. We're going to learn 4 steps of hypothesis testing, and we're going to apply those consistently regardless of what technique we're going to be utilizing. And that will allow us to test our hypotheses. So it's a very formalized process, much like the scientific method, right? It's a very formalized step-by-step, these are the things that you do. So here's our 4 steps of hypothesis testing. We're going to state the hypothesis, we're going to set the criterion for a decision, and we're going to collect the data and compute our statistic. So we're going to run that analysis. And part of that is figuring out what analysis do I need to run, right? And then finally, we're going to make a decision. That might be worded just a little bit differently depending upon your edition of the textbook, but they're all pretty much the same thing. First, state our hypothesis. What's our null? What's our alternative? You'll learn what those words mean in just a bit. Our criterion, we're going to kind of set it up. What alpha level are we going to use? What does that mean for our boundaries for the critical region? So all those exercises that you've done in chapters 5, 6, and 7 will all be kind of coming together for hypothesis testing. And then we're going to have to determine which technique do I use. You will have learned 2 so far. You've learned a z-score, where you're just using standard deviation, and that allows you to compare a single person to the rest of a group, right? And then you've also learned the one with standard error, and that's when we're comparing a sample to a population. But in both situations, I know both the mean and the standard deviation of my population, okay? And I have to make a decision. And so you're gonna learn new terminology in this chapter: a null hypothesis, an alternative or a research hypothesis, fail to reject the null, type 1, type 2 error. You're gonna learn a lot of terminology in this particular chapter, okay? So here goes. When we talk about state the hypotheses, there's 2 different types of hypotheses. All statistics, all of inferential statistics are based on the null hypothesis. We're always testing the null hypothesis. Null means just that, nothing, nada, zip, 0. It's predicting no differences, no changes, no treatment effect. The drug didn't work, nothing happened, okay? We notate null hypothesis with H subscript O, okay, or 0 actually. And it is the absolute most important critical hypotheses of the 2 from a statistics standpoint, because it is the basis on which we can mathematically test the null, and we can reject the null or we can fail to reject the null. The alternative hypothesis is typically the motivation for our research. It is our research hypothesis. We predict this drug is going to help, right? And so we are motivated and compelled to do the research because of this alternative hypothesis. We're saying, no, it's not nothing, it is something. It matters, it makes a difference. So it is the alternative to the null, okay? So in the null, we say nothing happened. In the alternative, we're saying, no, something meaningful happened, okay? And so this is our research hypotheses. And we can't mathematically test the alternative hypothesis. Why? Because there could be a million, an infinite number of outcomes beyond 0, right? I can't test every possible outcome, but I can test no differences. So your formulas are all structured around the null hypothesis, assuming there is no difference between the individual participant and the group, or between the sample and the population, or between 2 groups. The null assumes there is no difference. Your treatment did not work. It had no effect. It was 0 effect, okay? The alternative is saying, yes, there was something greater than the null. And so we want to truly be motivated to find this alternate, right? Why am I going to give you a drug if I don't think it's going to work? But mathematically, I can only build my formula around the null. So how we notate the alternative is H subscript 1, okay? So this is the null, and this is the alternate hypothesis, okay? And what we're doing in our alternate hypothesis is we are saying, we're predicting that the independent variable did in fact cause changes in the dependent variable. That my drug worked. It caused you to be happier. It helped alleviate your anxiety. Whatever the intended purpose of that drug, it worked. My treatment worked. If my therapy is supposed to help improve marital satisfaction in couples, then I am hoping that, in fact, after 6 weeks of therapy with me, my couples are happier in their relationship. That is what's motivating me to do the research. But statistically, I'm centering my mathematics around the null, okay? Okay, now the second step in hypothesis testing is set the criterion. This is a new terminology for you. Remember how I've talked about when we go to our, and let me just go there and draw it out, and we'll sketch it out and it'll be familiar to you, right? And we are drawing this out, and you've seen me say this now a dozen times or more, right? That you have your mean, and you have about what percentage now falls in here? Originally we said 70%, but now we know that it's actually what, 68.26%, I think, right? And then we talked about within 2 standard deviations, what percentage? About 95%. We now know that's just a tad more than 95% of the population. So our focus then in statistics is these ends, these margins, what we call the critical region, okay? And I told you that you can set different criterion. The criterion is your alpha level, okay? That is basically the percentage that you're willing to leave in the tails for your critical region. And commonly, we want to work with an alpha level. Let me just erase that. Commonly, we want to work with an alpha level of 0.05, okay? And that would mean that the 95% in here, right? And then 5% in the ends, okay? We can also set a criterion of, I'm gonna make this orange, 0.01. And if we're doing 0.01, then the middle isn't gonna be 95%, it's gonna be 99%. And then here is gonna be just 0.5%. Because together, these 2 ends now are going to make up the difference of that 99%. So they'll total 1%, and then the 99% will be in the middle. And what happens is that now makes our critical region smaller, right? It pushes those boundaries out further, and it makes our critical region smaller because we're giving up the 4%, right? So it's giving 2% more to be in the middle, and then it's giving, it's reducing, instead of being 5%, 2.5%, it's reducing it down to just 2.5% on the end, okay? And so this is what's called our criterion, our alpha level, okay? This is what's called our criterion, or our alpha level. And what we're saying is we will only allow a probability of less than 5% or less than 1%. That's how certain we want to be that our treatment worked, that our independent variable did in fact cause a change. Is we want them to be unlike the rest of the 99% or the rest of the 95%. We want them to be in those outer 5% of the population, or in the outer 1% of the population, okay? Most often, I will default to 5%. That's what I'll often default to. In this class, that's what I'm gonna teach you, is a 5%. And we know when we look at the unit normal table, and let me just go there. When we look at the unit normal table, oh damn, I'm not seeing it. So give me just a second and let me stop sharing. And then I'm gonna go find my unit normal table really quickly. I'm just going to go back into our class and pull it up. So I'm going to modules. I'm going to go to our appendix, and it's Appendix B, and I'm going to open that up. Okay. And so now I'm going to go back to our class, and I'm going to share the screen, and I'm going to share that unit normal table. Now, when we're looking at this unit normal table, I want to look for the z-score that corresponds to 5% in the tails or 1% in the tails, okay? So I'm going to focus here on column C for proportion in the tail, and I'm going to scroll down until it gets to 5% and 1%. And we already know what the boundaries are for 5%. They are the 1.96, remember? Here we go. That's about 0.025 in the tail. So if it's two tails, because remember it's on both sides, then together it's 5%, okay? So it's 2.5% on this side and 2.5% on that side. And together, that is 5%. So our z-scores, when we're using an alpha level of 0.05 or a criterion of 0.05, then our z-scores are going to be plus or minus 196, okay? So I'm going to come back to that. Now I'm going to look for, remember I want the other alpha level is 1%, which means in the tail I have to divide that by 2. If it's a two-tailed test, it's going to be 0.5%. And so now I want to look at what takes me to 0.5%. And it's going to be about, do I want to go a little bit lower, a little bit higher, but about 2.58. So 1.96 and 2.58, okay? So let me go back here, and I'm going to take you back. And so now what I'm saying is, with an alpha level, and that's the alpha symbol, okay? Let me go back and go ahead and just make this black so it stands out a little bit better. So with an alpha level of 0.05, then my boundaries are plus and minus 1.96, okay? With an alpha level of 0.01, then my boundaries are, what did we say, 2.58, I think we said? So I have to have scores that are beyond those boundaries in order for it to be in the critical region, okay? So those boundaries are going to be really important moving forward. And I want to give you just a little bit of heads up. I'm going to go ahead and clear this. When we set our boundaries for our critical region, and we say 1.96, this is going to be negative 1.96 or positive 1.96. We've identified, we set an alpha level of 0.05, and we identify our boundaries to determine our critical region. This is going to be so important, because if our score's over here, it's not in the critical region. It's just like the other 95%. So what we say is, we say that it is not statistically significant. And we say the probability of getting this score was greater than 0.05, right? Because if it were less than 0.05, it would be in those critical boundaries, okay? Now, if it's in either over here or over here, then now we say it is statistically significant. And it is a probability of less than 5%. Because remember, in here is 95% of the population. And then over here is 2.5, and over here is 2.5, for a total of 100% of the population, or 100% of the pie, okay? So what I'm really trying to figure out, my null hypothesis is saying it's going to be in here. So I'm going to do null. My null hypothesis says it's going to be in here, right? There's no differences. My alternate hypothesis is saying, no, it's going to be over here in these critical regions, okay? Make sense? This is what we call a two-tailed hypothesis test. And I'm going to come back to this in just a bit. But for now, I'm going to go back to our original lecture, okay? Okay, so we want to set the criterion, and that's choosing our alpha level. How big do we want those critical regions to be? How small do we want those critical regions to be? And that's the researcher's decision. I'm going to tell you how you make that decision. You read other studies, right? We don't just pull our hypotheses out of our ass. What we do is we have a research question and we read the literature and we pull up other studies and we see what other research has been done and what they've found. And then based on that information, we have an educated guess or a prediction, a hypothesis of what will happen in our study. And as we're reading those studies, if they're all using 1% and then you use 5%, they're going to be like, whoa, no, our standard is 1%. So you need to make sure you're adhering to our standard. So you're going to follow the standard that applies in your particular field that you're studying. I will tell you, when I was a student, they had 10% alpha levels were very common, and 5% was conservative. Nowadays, 0.01% or excuse me, 1% is conservative. So an alpha level of 0.01 is conservative. They are even commonly using an alpha level of 0.001, okay? So know that you're gonna look and see what other studies have done. When we were just talking about kind of a general rule of thumb, we were just saying anything greater than 2, a z-score of 2 is in the critical region. Now, if we get into the nitty-gritty and we find the z-score based on what we learned in the unit normal table, we find a z-score that corresponds to 5% in the tails combined, so 2.5 on one tail, we know it's plus or minus 1.96, okay? So again, if it's in that critical region, there's a very low probability of getting a score in that critical region. Most scores are going to center around the mean, right? They're going to fall pretty close to what the population mean is. But if we've given them a drug, then it stands to reason that if our drug worked, sorry, I have something in my eye. If our drug worked, then it's going to cause our sample to be different than the rest of the population. It's going to cause ours to be unique. So we're going to expect it to fall into the critical regions, okay? Okay. So if it's the null hypothesis, it's going to fall in here. If it's affirming the alternate hypothesis, it's going to be in the critical region. We don't really, in research, we don't really say, oh, it is, you know, we failed to reject the null. We don't use that terminology, but you have to understand that terminology from a statistics standpoint, because remember, our statistics are all built around the null, okay? So when we're talking about a critical region of 5%, it's 2.5% in this tail, 2.5% in this tail for a two-tailed test. So 95% of the scores are expected to fall in this middle 95%. And then the other ends, it's going to be anything greater than a 1.96 or lower than a negative 1.96 is said to be in the critical region. When it's in the critical region, we reject the null hypothesis. Remember, null is symbolized by H subscript 0, okay? So we reject the null. The null is false, which means our alternate is true. In the middle, if it falls in the middle, that means our null is true. It's just like the rest of the population. It's no different. Nada, 0, zilch, right? That means we failed to reject the null and our alternate hypothesis is wrong, okay? In research writing, we say it's not statistically significant if it's in the middle. If it's in the critical region, we say it is statistically significant, okay? Okay, great. Let's there we go. So we set our criterion, which means we're choosing our alpha level, which is also known as our significance level, right? And we're saying, what's the probability of getting this number? We want to set that probability low to hold ourselves to a high standard, right? So if I'm in a push-up contest and I say, okay, I'm going to be able to do 100 push-ups, I'm setting a really high bar. But if I set it at low and say, oh no, I just want to be able to do 10 push-ups, and then that might be more achievable. Shit, I might need 5 push-ups. So our alpha level sets that significance level, okay? What's the probability? Is it very likely or unlikely? We're setting a criterion that makes it unlikely to get that score because that says our treatment really worked, okay? If I wanted to say, okay, working with a trainer improves your upper body strength, but I set a criterion of just 3, being able to achieve 3 push-ups as my test, pretty much most people in the world, 95% of the population can probably do 3 push-ups, right? But, you know, I want mine to be in the 5%. I want to say, no, my training made them different than the general population. It significantly improved their upper body strength. And so therefore, I want a criterion like 15 or 25 or 30 push-ups that really show that my training causes my participants to be significantly different than the general population, okay? So as I mentioned, the most common ones that you see, notice this is an alpha level, it's like that fish. Again, we're talking about Greek letters, right? Alpha level of 0.05 is what I'm going to default to, but commonly in the research, you'll see 1% and 0.001, okay? Okay, so let's move on. Here are the Z-scores for a two-tailed test. If we're doing a 5% alpha level, our corresponding boundaries would be plus or minus 196. If we're doing a 1%, we look this up, it would be 2.58. And if we're doing 001, the corresponding boundaries are 3.30. Notice that when I set a lower alpha level, I'm making my critical region smaller, right? Which means I'm pushing those boundaries out further. So more people are in the middle here and the edges are smaller, okay? Okay. So my third step is going to be to collect the data and compute the statistic. Now, I know my design. I know what type of data I'm collecting. I know my independent variable, my dependent variable. I'm applying my test, measuring things. The trick for a statistician here is knowing what technique applies to what design and what research question based on the data that you've collected. So you're going to have to figure out as a statistician which technique to use, okay? Right now it's going to be easy. You only have 2 to choose from. You have the Z-score where you're comparing an individual participant to the rest of their group, or you're comparing a sample to the rest of the population based on a distribution of means, okay? So you only have 2 choices. Our formula here is comparing the mean for our sample to the population divided by a standard error, or if you're comparing one individual participant to the rest of their group, it would be the X minus the mean divided by the standard deviation, okay? Okay, and so then we have to make a decision, and we have 2 decisions to make. We can either reject the null, and that's if it's in the critical region, we reject the null. That means it's statistically significant. It is different than the rest, the majority of the population, okay? That means our treatment worked. Our IV did something. Our personal training did something, okay? If it's not in the critical region and it's in that middle 95%, then we failed to reject the null. It is not statistically significant. The probability of getting that was greater than 5%, so it really didn't mean anything special, and our treatment did not work. It did not cause them to be statistically significant or significantly different from the rest of the population, okay? So that's where I'm gonna go back here, and I'm gonna go to, if it is here in the critical region, right? It's beyond this boundary that I set of 1.96, it's statistically significant, and I am going to reject the null. If it's not statistically significant and it's here in this middle part, 95%, then I'm gonna fail to reject the null. Remember, everything centers around the null because statistically, my formula is based on the null. Even with the z-score, I'm comparing differences between the sample and the population. Everything is based on the null. Okay, so let me go back to my, presentation. Okay. So we have two possible outcomes, reject the null or fail to reject the null, okay? And that terminology I know is confusing. If it's in the critical region, we reject the null and P is less than. The probability of getting that score was less than 0.05. If it's not in the critical region and it's just in that middle 95%, then we fail to reject the null and our probability of getting that score was greater than 0.05. So it didn't meet our threshold or our standard of significance. And this terminology, reject the null and fail to reject the null, can be really confusing for people. But because our formulas all center around disproving the null, that null terminology is important for you to understand, okay? So why do we use it? I'm going to give you a jury trial analogy. We don't say when we determine whether we're on a jury and we're hearing a case against a defendant or hearing the evidence, we go and deliberate and we come back. We don't say guilty or innocent. We say guilty or not guilty. We assume they are innocent. We assume the null. We assume that the prosecutor does not have enough evidence and they did not do anything wrong. That's supposed to be the assumption, that they are innocent until proven guilty. And it is up to that prosecutor to provide enough evidence beyond a reasonable doubt for us to say there is enough evidence to say they are in fact in the critical region, that's outside the norm, and they are guilty, okay? But if they are not, if the prosecutor has not met that burden and has not provided enough evidence, we don't say they're innocent. For all we know, they did it. There just wasn't enough evidence to say that they did it, right? So we as statisticians are basically saying there has to be enough evidence to reject that null. That's equivalent to a guilty verdict. We have to make sure that we're saying we have enough evidence. So we want to set a criteria that says we want a less than 5% chance that you're wrong, that we're wrong, that you are, that there was less than a 5% probability of getting this score. So therefore, it's different than the rest of the 95% of the population. It's different, it's unique. So that 5% essentially is how much we're allowing for reasonable doubt. We can reduce it to 1%. We can reduce it to 0.001 if we want to. But that's our allowance for reasonable doubt. How big or how small are we going to make those critical regions, okay? And we have to gather enough evidence to reject that null, to say, yes, there is enough evidence here, guilty, okay? But we don't say, oh, there's not enough evidence this person is innocent. We say they are not guilty. We fail to reject the null. So rejecting the null is equivalent to a guilty verdict. Failing to reject the null is equivalent to a not guilty verdict, okay? Okay, so here's a little learning check for you. Go ahead and pause me and take some time to answer this. Okay, so a small value near zero for the z-score statistic is evidence that the sample data are consistent with the null. So think about that normal distribution. A small z-score is going to be closer to the middle, and it's our edges that are going to be able to reject the null. So closer in the middle is consistent with the null, supporting the null, and the edges are rejecting the null, okay? So that is going to be true. It's closer to the null. I mean, it's closer to the middle. It's closer to the mean. So it's going to be more consistent with the null. Okay. Number two, a z-score value in the critical region means that we reject the null. Yes. So in the middle, we fail to reject the null. In the critical regions, we reject the null. This is greater than 5% probability. This is less than 5% probability. This is not statistically significant, just like the rest of the population. This is statistically different, significantly different from the rest of the population, okay? Okay, here's another learning check. Go ahead and pause, read through it. Okay, if you restarted me, here we go. The city school district is considering increasing class size in the elementary schools. However, some members of the school board are concerned that larger class sizes may have a negative effect on student learning. In words, what would the null hypothesis say about the effective class size on student learning? The null hypothesis would say there's no difference. It doesn't matter. It doesn't have an effect. So it would say class size has no effect on student learning. So we wouldn't find any difference in student scores in the small class compared to the larger class. There would be no differences, null, near and zero, nada, zilch. That's what null means, right? If a researcher conducted a hypothesis test with an alpha level of A or alpha is equal to 0.02%, what z-score values would form the boundaries of the critical region? And what we have to do here is we have to go to our alpha level. And if it's a two-tailed test, we know that if it's 0.02 on both ends, then it's only 0.01 on the other end. So we're gonna have to look up proportion in the tail at 0.01, because together we want it to be 0.02. And that's going to be right here, 2.33, 2.232. So that would be plus or minus on both sides of that distribution. So the z-score would be, and you get to decide which one you want to go with. I'd probably go with a 2.33. And then I'm going to take you back to our lecture. And so here you go, 2.33. Make sense? Okay, one more learning check, so go ahead and hit pause. Okay, starting me up, a researcher selects a sample of 16 individuals from a normal population with a mean of 40 and a standard deviation of 8. A treatment is administered to the sample, and after the treatment, the sample mean is now 43. If the researcher uses a hypothesis test to evaluate a treatment effect, what z-score would be obtained for this sample as the critical boundary, okay? So I basically want to know my critical boundary for less than 5%. I already know it's going to be a 1.96 as my critical boundary, but where is this going to fall, right? So what I first have to do, I'm talking about comparing a sample to a population, okay? And I know this is a sample, it's not an X value, it's a mean. So I know it's a sample. So the first thing I'm gonna do is I'm gonna get my standard error because I'm dealing with a sample, I'm dealing with a group and not a single individual, so I have to use standard error. My standard deviation was 8. I had 16 people in my group. So that's going to result in a standard error of 2. I'm going to plug that into my z-score to find out what my corresponding z-score is for 43. And I'm going to see if my 43 extends beyond those critical boundaries. And so I'm going to plug it in. My mean was 43 minus the sample, or excuse me, the population mean of 40 divided by my standard error of 2. I now see that my z-score for my 43, my sample, was 1.5. So let me take you back to our whiteboard. And if I said, oops, let me erase that. If I said that I'm going to do an alpha level of 0.05, so that means my boundaries are going to be 1.96, negative 1.96, right? I know that this would be 0 because I know the mean for all z-score distributions is 0. And I said that my score in particular, I'm going to make that blue, was 1.5. That's probably somewhere around here, right? That was my z-score. So is it in the critical region or isn't it? It's not, right? The critical region would have to be on the boundary, and it's not. So it's with the other 95%. It's not in that 5% range. So then what happens is, what do? I fail to reject the null. How I write that up is I say that my sample was not statistically significant, or it was not significantly different from the rest of the population. And I failed to reject my null. The probability of gaining my score was greater than 5%, okay? If by chance it would have been, let's say, 2.5 over here somewhere, then yes, I would reject the null. And I would say that it is statistically significant. So it's significantly different than the population. The probability was less than 0.5, okay? So, but because it's not in the critical region, it doesn't meet that threshold, okay? Okay, so that's hypothesis testing. In this case, I'm supporting my null hypothesis and I am not supporting my alternate hypothesis. Okay, so I'm going to go back to sharing my screen and let's look and learn some more. Yeah, it takes a little while. Okay, so whenever you're making a decision and you're deciding guilty or not guilty, well, you could be wrong or you could be right, right? And so if I say guilty, I could be wrong and I could send an innocent person to jail, or I could be right and they were in fact guilty and they deserve to rot in jail, okay? Or I could decide not guilty and I could be wrong when I let a guilty man free. Or I could be right and they really didn't do anything and they got off, okay? And that's, you know, ultimately you want to be right. But there's always the possibility of being wrong. So how do we minimize the possibility of being wrong? And we try to do that mathematically. So being wrong in either one of those situations, we have names for that. A type 1 error is when you have rejected the null. You said they were guilty. There was enough evidence to say, no, there's enough evidence to believe that they did something wrong. They're in that critical region. You rejected the null. And so you said, absolutely, they did it. Okay, well, that could be dangerous in the criminal justice system because you could, if you're wrong, you just sent an innocent man to jail, right? That's what we call a false positive. I said that the test worked when it really didn't. I said that they are in fact guilty when they really weren't. I said there were differences when they really weren't. That's a problem. What if I'm testing a drug and I'm looking at this drug and its effectiveness in treating cancer? And I said, yeah, my drug works. So people start taking my drug when it really didn't work. It was false. It was a false positive. That means they're not taking other drugs that could be working, that could be helpful. So that's dangerous in research. So the most dangerous error that you can make is a type 1 error. We do not want to send an innocent man to jail. We would much prefer to set a guilty person free than send an innocent man to jail. So type 2 error is actually the opposite. It's saying, no, there aren't any differences, right? I'm failing to reject the null. I'm saying, yeah, that null's true. I'm affirming it, that I can't find any reason to find that there are differences. It's a false negative. It's saying, nope, there's no differences. You're not pregnant. There's nothing in this urine. It's saying that, you know, I'm not finding anything significant enough to say that you're guilty. So I say not guilty. I fail to reject that null. But when in fact, you really did it, okay? We would much rather as researchers make sure that we're not sending an innocent man to jail. So type 2 error is important, most definitely. How we control that is sample size. We try to make sure that we have a big enough sample to detect differences. How we control for type 1 error is through our alpha level. We want to minimize that probability because the probability of finding the result is based on the alpha level. It's saying, how big do I want my critical region? I'm setting an alpha level of 5%, but that means I'm also running the risk that I could be wrong that in those 5% of cases too. And so I can reduce my risk of type 1 error by making my alpha level smaller and reducing it to a 1% probability instead of a 5% probability, okay? And so with a type 1 error, we can control that through our alpha level. And our alpha level is the probability of finding our number, but also the probability of being wrong about our decision. A type 2 error is when we fail to reject the null in error. We don't find enough evidence when in fact the person really did it, okay? And that means our sample mean wasn't in the critical region, but maybe we just didn't have enough information. Maybe we didn't interview enough witnesses. We just didn't gather enough evidence, right? But maybe they were in fact guilty. And so what we try to do for that is make sure our samples are large enough so we're gathering as much evidence as possible so that we can find differences if they really do exist, okay? And so we associate type 1 with our alpha level. We associate with our type 2 error with our beta. So alpha and beta, the two go together, okay? I can, again, reduce the risk of type 1 error, but when I do that, when I make those critical regions smaller, so I don't make a type 1 error, I'm increasing my risk of type 2 error. Because now I'm making those boundaries for the reject the null bigger, which means that I have a harder time. My criteria is more stringent, or I'm raising the pole if it's a high jump, right? And so I may not be able to get over that pole because my standard's so high. And so that also has a negative effect. When I reduce my risk of type 1 error, it increases my risk of type 2 error. So here's a visual chart if this helps you. So I can make two decisions. I can either reject the null or I can fail to reject the null. And that can either be correct or incorrect, right? If I reject the null when in fact there really was no treatment effect, so the null is true, then that, and I reject it, when the null is true, I shouldn't be rejecting it. I should be retaining it, right? So that's when I make a type 1 error. If I reject it and there is in fact a difference, right? Our null is false, then I made the correct decision. If I fail to reject, so I said not guilty, But in fact, the null was true and there wasn't enough evidence really, then, or excuse me, I failed to reject the null and the null is true, then that's a correct decision, right? I said not guilty, there wasn't enough evidence, they really aren't guilty, that's a correct decision. But if I failed to reject the null and I'm saying they're not guilty when in fact they were, that's a type 2 error, okay? So type 1 error is equivalent to sending an innocent man to jail. I rejected and said they were guilty when I really didn't have the evidence. And then type 2 is equivalent to saying not guilty, I failed to reject, but in fact, they really did do it, okay? Okay, so a couple of tricks that some students in the past have come up with for remembering type 1 versus type 2 error is this fire alarm. If you think of type 1 as a false alarm, it's your alarm going off and telling you, yeah, there's a fire, there's smoke in the house, when in fact there's really not. It's a false positive, okay? So it's telling you that there's something's going on when it's not. Type 2 is like the house burning down and the fire alarm never going off. It's a false negative. It's not telling you that there's something there when in fact there was. So it missed it. It did not detect the evidence of a fire, and so, you know, it's bad. So type 1 is saying there's a fire when there's not, is a false positive. Type 2 is a false negative, saying there isn't a fire when there is. I kind of don't like this example because it makes type 2 sound more dangerous and scary, and it makes it seem like type 1 is not as scary, when in reality as researchers, we really are more concerned about type 1 than type 2. And so that's why I like the guilty, not guilty analogy better, but you do you. Another person came up with this roar, like a lion thing. So type 1 comes first, 1 comes before 2. So if we look at the acronym, so you reject the null when you should have accepted it. So that's type 1. And the second part of the R is type 2. You accepted the null when you should have rejected it. Okay, so those are tricks. If those work for you, great. If they don't, come up with your own. I like my guilty, not guilty analogy, but you do you. Okay, so when we're talking about hypothesis testing, we need to state our hypotheses and select an alpha level, right? So based on an alpha level of 5, 1, or 001, we will write out our null hypothesis. I expect my mean of my sample, expected mean, to equal my population mean. I'm not expecting any differences. There are no differences between my sample and my population. You always write your null statistical notation in parameter form. And we do that because inferential stats, our whole purpose is to make inferences about our population based on our sample. And so we write statistically in terms of population or parameters, okay? So our null is saying there's no difference between our expected mean, which remember that's the mean of the distribution of means, right? There's no difference between our expected mean and our population mean, whereas our alternate hypothesis, we're saying those two don't equal one another. There is a difference between the two, okay? Then we locate our critical region and set our boundaries. So some people just state the alpha level here, and maybe number 2 is where they select the alpha level and locate the critical region and set those boundaries. It doesn't matter whether you do it in step 1 or step 2. It just needs to be early on, okay? But I locate my critical region and I already know the boundaries for a two-tailed test for a 5% alpha level is going to be plus or minus 196, 1% plus or minus plus or minus 258, and then 0.001 plus or minus 3.30. Now I compute my t statistic. So in this case, when I'm comparing an individual to the rest of their group, I'm just going to use the regular z-score formula. When I'm comparing a group, a sample to the population, then I'm going to use the z formula with standard error, okay? So first I have to calculate my standard error, and then I plug that into the z-score formula. And then I need to make a decision. Am I gonna reject the null or am I gonna fail to reject the null, okay? When I fail to reject the null, you can think of that as retaining the null, okay? But I have those two choices to make. I can be wrong or right in either one of those choices. If I'm wrong, and when I reject when I'm wrong, it's a type 1 error. When I reject the, when I retain the null or fail to reject, that's a type 2 error when I'm wrong, okay? So what we do in the literature is we don't usually, if you read a research study and you pull empirical studies or and you're reading them, they don't usually use verbiage like, oh, reject the null, fail to reject the null. They don't use that language. We use it as statisticians because we know our formulas are centered around the null, but we actually don't report it that way. We report our results by saying it's either significant, it's statistically significant, or it's not. We do not usually say, you know, that we're gonna reject the null. So here's an example down here of how we might report something. Electrical stimulation of the scalp near the parietal lobe had a significant effect on the mathematics test scores for students. Z equals 2.25. The probability of getting that Z score was less than 5%. So meaning that there's a less than 5% chance of getting this outcome, which is why it was significant, okay? So we use statistically significant rather than reject the null or fail to reject the null, okay? Okay, so let's talk about assumptions. This is the first time you're being introduced to assumptions. There's assumptions associated with every inferential technique that we're gonna use. And the assumptions are essentially the criteria that has to be met in order for that test to be valid, okay? So you can still use it if you violate assumptions, but it just gives other researchers the opportunity to critique your findings, okay? So in a hypothesis test, when I'm using Z-scores, I am assuming that you engaged in random sampling. I am assuming that your participants were randomly selected and then you didn't go and target specific groups that might have characteristics that are consistent with what you're looking for. I'm also assuming independent observations, meaning there's not a predictable relationship, and that if you're using a random sample and I'm using random sampling with replacement, right? Then this is usually met automatically, where the outcome for participant B was not impacted by the outcome for participant A. They're independent of one another, okay? Also, I'm assuming that the standard deviation is the same. The treatment did not affect the standard deviation. I have about the same average distance from the mean, both before and after the treatment, okay? And then I'm assuming that it's a normal sampling distribution. Your original, the original distribution doesn't have to be normal, but a sampling distribution, every possible sample given n equals x, right? Whatever that might be, 2, 4, 6, whatever it might be, every possible combination of 2 is going to create a distribution of sample means now, and that distribution of sample means is normal, okay? Okay, so when I get into the Z-score for a hypothesis test, again, you have to think about your test statistic. In this case, it's simple because we only know a couple tests at this point. But as we learn more tests, it's going to be harder to figure out which test statistic makes sense, okay? But it's what technique are you going to use to test your hypothesis? So using Z-scores is an example of a test statistic or an inferential technique. And it serves as a really great model and foundation, and that's why it's done early on, because that unit normal table is great for us to see how we can use probabilities to make predictions, right? And then you're gonna use this as kind of a recipe, and we're going to follow these same steps and guidelines moving forward, okay? And then our formulas are basically looking at the difference between the sample mean and the population mean. And remember, we're testing the null. If this were 0, then our z-score, we would not show that our z-score is significant, okay? If there's no difference between the sample and population, it would not be even near the critical region, okay? But if there's an actual difference between these two z-scores, that gives our chance of our z-score being higher and therefore in the critical region. So larger z-scores indicate that the null is probably wrong. We're probably going to reject it. Smaller z-scores closer to 0 indicate the null is probably true, and it's just like the other 95% of the population. So let's look at things that can actually influence a hypothesis test. The mean difference. The bigger the difference between the sample and the population mean, the more likely you're going to reject the null. You're going to have a larger z-score because that's going to mean a larger numerator, right? Also, you have to think about the denominator affects it as well. And that variability of scores, remember that denominator is affected by standard error, which is affected by standard deviation. And standard deviation is the average deviation from the mean. And so if it's bigger, right, that means your denominator is going to be bigger. And that's going to mean your z-score outcome might be smaller. So when you have a lot of variability and your standard deviation and your standard error is bigger, then it's going to have lower z-scores. Now, one of the things to kind of keep that standard error small is having a larger sample size. Because remember, if you look at the formula for standard error, it's impacted by sample size. And so sample size, if you have bigger samples, it's going to give you a smaller standard error. So your denominator and your z-score formula is going to be smaller, and it's going to give you a bigger z-score. So z-scores are going to be larger if there's a larger mean difference, if there's a lower standard deviation, and if you have a larger sample size, okay? Okay, now so far we've been looking at two-tailed tests, and we call those non-directional tests. In other words, I'm not predicting which direction my score is going to be. I'm not predicting it's going to be in the critical region, so my scores are going to be higher than the mean, or it's going to be in the critical region on the other end where my scores are going to be lower than the mean. That's called a non-directional test, a two-tailed test. You can also do what's called a one-tailed test, where I'm predicting a specific direction. So let's say I know that growth mindset reduces anxiety. So I'm going to do your anxiety. I'm going to measure your anxiety. I'm going to teach you about growth mindset, and then I'm going to measure your anxiety again. I'm going to expect your scores to go down, right? And so then I would have a directional hypothesis test. So if in my theory, if the other research is solid and allows me to make a prediction in one direction or the other, then I can use what's called a one-tailed test. And a one-tailed test is a directional hypothesis test. And what that means is I'm going to pile up the probability on one side or the other. And let me show you what I mean by that, okay? So I'm going to go to, give me just a second, our whiteboard. And let me clear this. Okay, so if I'm using a two-tailed test, okay, and I'm doing an alpha level of 0.05, okay, and I'm setting my boundaries so that combined my critical regions equal the 5%, and in the middle, it's 95%, okay? Then what I'm doing is I'm dividing up that 5% by either end. However, let's say I want to do a one-tailed test or a directional test. What happens now, because this is only 2.5 and this is 2.5, together they make up this 5%, okay? Together they make up this 5%. Let's say that I want to do a one-tailed test, okay? And I'm expecting my scores to go down. My anxiety scores are gonna go down. I'm expecting them to go in a specific direction. So if I do a one-tailed test, I don't have to worry about this side over here. All I have to worry about is the left side of my distribution. So now my whole 5% can be over here. So now I get another 2.5%, and now my 95% includes this other end or other tail. So now I get to focus on a bigger critical region on the side of the distribution that I'm predicting my scores will go. So now I can look up the Z boundary that doesn't have 2.5 in the tail, but now has 5% in the tail. And so if I do that, remember my original boundary was negative 0.196, and now I can go to my unit normal table and I can find what the Z-score is for 5% in the tail instead of 0.025% in the tail. And I'm gonna look over here. I'm gonna stick right here to the 1.65, right? It's less of, it's a lower Z-score value that gets me into the critical region. So watch, I'm gonna go back. And now the Z-score only has to be below 1.65. So I've gained some extra space in my critical region. Does that make sense? I hope so, I hope so. You can do your reading and you know, take really good notes. I'm gonna always teach you from a two-tailed test, but understand at any time you can use a one-tailed test. And you know, some people might be saying, well, when do we use a two-tailed test and when do we use a one-tailed test? It really depends on the theory and your research question and what existing research says. You know, if you have a strong probability that it's going to go in one direction, great, you can do a one-tailed test. But the challenge is, what if it goes in the other direction? You just lost that opportunity to detect differences. So it really depends. It's up to you whether you want to do a one-tailed or a two-tailed test. We're still going to follow the same exact steps. Whether you're doing one-tailed or two-tailed, you're going to follow the same steps of a hypothesis testing. Only when you get to that point of identifying your boundaries, instead of having plus or minus, you're either going to have a plus Z-score or a negative Z-score, and that boundary is going to take up the full alpha level in that tail rather than splitting that alpha level between the two tails. Okay? Okay, so this is just going to take you through an example. I'll let you kind of read that on your own. And then here's a couple learning checks for a one-tailed test. Again, same process, so I'll go ahead and let you do that on your own. I do want to get to effect size, and I'm going to tell you I have a completely separate lecture on effect size. So I'm going to let you watch that lecture, but I'm going to just give you the gist of it, okay? The Z-score test itself, the inferential technique itself, lets us know whether it's in the critical region or not. But it doesn't tell us the magnitude of the treatment effect. It lets us see that there was a treatment effect, the treatment did work, but it doesn't tell us how strong the treatment effect was. So it's equivalent to something like, it lets us detect an earthquake, but it doesn't let us determine the size of the earthquake. If we really want to determine the magnitude of the treatment effect or the magnitude of the earthquake, we're going to use effect size. Effect size is a really important measure. Almost all research studies in modern day times use effect sizes. So they first calculate the technique, the results for the technique they're using, in this case, Z-scores, and then they do a follow-up calculation to calculate the effect size that corresponds to that Z-score. And they report both in their research paper. And so if you look at old studies, like 30 years ago maybe, effect size wasn't automatically done. It was done for like meta-analyses or something like that. But now it's a standard of practice to take that extra step and test the effect size and the magnitude of your variable. We have different techniques we use. So not only are you going to be using different inferential techniques that are going to help you determine whether you're going to reject your null or not reject your null, you're also, once you reject the null, you're going to find out, you're going to have a variety of effect size techniques that you can use. The one we're going to learn about for z-scores is Cohen's d. And Cohen's d is a great fit because Cohen's d tells us what the treatment effect was in terms of standard deviations. Specifically, it tells us how our treatment effect, the magnitude of our treatment effect in standard deviations. So it increased our treatment effect by X number of standard deviations, or it decreased our treatment effect by X number of standard deviations. And so it's a really great effect size to correspond to z-scores. Now, I'm going to tell you, and this is just a visual illustration of, here was our treatment effect, and then here was our distribution of scores. But after administering our treatment, it literally moved it over because it impacted. This was the magnitude. It shifted us over. And this is just a D of 0.15. And this is saying, look, in this one, the treatment moved it over and shifted it by a whole standard deviation. So when the D value tells you the number of standard deviations, the treatment shifted the effect. And I'm going to tell you, the bigger the D, the better. Okay. Now, a lot of people take that sexually, and I imply it sexually because it's a great memory mnemonic. Some people say size doesn't matter. In statistics, size matters, especially with effect sizes. Size matters, okay? So the bigger the D, the better. The bigger the Z, the better. The bigger the D, the better. If it's a bigger Z, it's going to be more likely to be in the treatment, in this critical region. And the treatment is going to be significant, right? We're going to reject that null. The bigger the D, the better. It means that it's having more of an impact or a greater magnitude on the outcome. And that's what we want, right? We don't want it just to reduce your anxiety a hair. We want it to reduce your anxiety by a significant amount, okay? So how do we calculate D, Cohen's d? We calculate Cohen's d by looking at that mean difference between your sample and your population, and we divide by standard deviation. And ultimately, it's telling you the number of standard deviations that your treatment caused the change, okay? So how many standard deviations were caused, or how much movement was there in terms of standard deviations? So it's a really cool measurement for us. And if D equals 0, there's no effect. It's like saying, yeah, no, there was not an earthquake. I'm sorry. So a positive D score indicates it increased your treatment effect, moved the scores up above the mean. A negative D means it reduced it below the mean, okay? But it's still, it doesn't matter. The positive or negative sign isn't telling us about the magnitude of the effect, it's just telling us the direction of the effect, just like a Z-score. But the number itself is telling us the magnitude of that effect. How many standard deviations did it cause your scores to move? And so here's a chart that's been determined to say what's a small effect, what's a medium effect, what's a large effect. And actually, if you're thinking D sexually and you're thinking, okay, the D stands for an appendage, right? It's standing for penis. Well, the average penis size is actually 5 to 7 inches. That's kind of middle of the road, 5 to 7 inches. So this chart can really help you, because if your D is at 2.2 or below, then it's small effect. A medium effect is 0.5 to 0.79. So it fits right along the line of our averages. A D of 0.8 or above is a large effect, okay? So great chart that helps us to determine whether it's a small, medium, or large effect, and we report that, okay? So a couple opportunities to practice this. I'm gonna let you do these learning checks in the other videos if you want, walking you through the calculation. I'm gonna tell you we do not calculate effect size unless we know we're rejecting the null. So if at step 4 of the hypothesis test, you're not rejecting the null, then you don't do an effect size. You only calculate effect size after you've rejected the null. So we have all the data we need from doing our inferential technique to calculate our effect size, okay? And you also cannot, SPSS cannot do it for you. So you're gonna need to plug it in on your own. And then finally, we're gonna talk about power. That's also in the other video, but power is the probability of being able to find significance. It's your power to find the evidence you need to convict, okay? To find the evidence you need to reject that null and to have them in the critical regions. And so there is a test that we can do to say, well, how big, how much evidence do I need? How big of a sample size do I need in order to find significance? And it's based on a lot of hypotheticals, okay? So if I say I want an 80% probability of finding a treatment effect, and I want my treatment effect to be X, Y, and Z, right? Then I can plug it into this formula and I can ultimately predict how large my sample needs to be in order to find that result. And so I plug it into a lot of hypotheticals. I've added some extra resources on the course shell, and they are giving you a couple lectures on power and a power calculator tool. So feel free to use those resources. When we talk about power, power is related to our beta. So it's connected to type 2 error, right? It's the opposite of type 2 error. Type 2 error is not finding differences when they do exist, and power is what's left over. What's my probability of finding differences, right? This is my type 2 is not finding differences, type 1 is finding differences, assuming they exist. And so we calculate power as 1 minus beta, okay? Okay, and so power is usually done before a research study has been conducted. Again, we're doing it to determine what steps need to be taken, how large does my sample need to be in order to find significance. So I'm doing it as kind of a preliminary analysis. It's kind of a complicated process. I actually don't know anybody who's ever done it by hand. I think Dr. Ullman did it by hand, but she actually just used a power calculator. So I went ahead and posted one of those online. But ultimately, I don't want my research study to be a waste of my time. I want to be able to have enough power to find a treatment effect. So it is a useful tool. Oh, excuse me. But it is not, it's not something I'm going to completely emphasize in this class. It's just something I kind of want you conceptually to be aware of, and then use outside tools to calculate it. It's not something I would ever expect you to do manually. As you can see, it's more complicated, okay? And then I just want you conceptually to understand power and effect size are related, right? Because if the treatment effect is smaller, I'm not likely gonna find it, right? If it's a really small earthquake, it can go completely undetected. But if it's a big earthquake, I'm likely gonna detect it. So I have more power to find it and identify it. Sample size matters. Bigger sample sizes give you more power and you're more likely to identify the treatment effect. Alpha level matters. If you reduce your alpha level so small, you lose power, okay? Whether you do a one-tailed or two-tailed divides your power across two ends, whereas one tail piles it up on one side. So it improves your power, okay? And I'll let you go through the learning checks on power in the other video. I'm gonna stop sharing. And then hopefully this helps you this helps guide you through hypothesis testing. Chapter 8's a really foundational chapter. So please make sure you come to me with any questions and if it's just not clicking for you. Otherwise, I hope you enjoy your first type of inferential technique. I'm looking forward to talking with you soon. Bye.